going to discuss an important concept in linear algebra called linear transformation. In simple terms, a linear transformation is a function that takes vectors from one vector space and maps them to another, while keeping the structure of vector addition and scalar multiplication intact. This means that the way vectors combine and scale is preserved under this transformation. Linear transformation are essential in various fields such as computer graphics, engineering, physics, and even data science. For example, when you rotate an image or scale a shape, you are applying a linear transformation.
And now, let's talk about the formal definition of linear transformation and its properties. A linear transformation is a function that takes vectors from one vector space called V and then maps it to another vector called W. For a transformation to be considered linear, it must satisfy the two properties. The first property is the additivity. This means that if you take the two vectors u and v and then add them together and multiply to the transformation t, you should get the same result as if you applied t to each vector separately and then add the results. The second one is the homogeneity or the scalar multiplication. This means that if you multiply a vector u and the scalar c and then apply the transformation t, the same as applying t first and then multiplying it to the scalar c. If both of these properties hold, then the transformation is linear.
Now, let's look at some examples of linear transformation. The first one is the identity transformation, which simply maps every vector to itself. It is t multiplied by x equals x. Next is the zero transformation. Zero transformation sends every vector to zero. It is t multiplied by x equals 0. The third one is the scaling transformation. It is where each vector is multiplied by a scalar constant, like t multiplied by x equals 3x. It is where it stretches or shrinks the vector. Geometric transformations like rotations and reflections on a plane are also linear. For example, a rotating vector around a origin by a fixed angle preserves linearity.
One powerful way to understand linear transformation is through matrices. Every linear transformation from r raised to the power of n to r raised to the power of m can be represented by an m times n matrix A, such that for any vector x in r raised to the power of n, t multiplied by x is equal to A multiplied by x. So, matrix multiplication here applies the transformation to x. This matrix representation lets us compute linear transformation efficiently and analyze their properties like invertibility and rank.
Sometimes, you're given a function and need to determine if it is a linear transformation. To do this, check two things. 1. Does it satisfy the function additivity? That's it. For any vectors u and v, does t times u plus v is equal to t times u plus t times v? 2. Does it satisfy homogeneity? For any scalar c, does t times cu is equal to ct times u? If both are true for all vectors and scalars, the function is linear. If not, the function is not linear. For example, t times x is equal to x squared is not linear because it fails these properties.
Linear transformation can also be understood geometrically. They always map straight lines to straight lines and map the origin to itself. For example, a rotation rotates vectors around the origin without changing their length. A reflection flips over a line. A scaling transformation stretches or compresses vectors along a direction. No matter what linear transformation you apply, Shapes like lines and planes remain flat and straight. They do not curve or bend.
To summarize, a linear transformation is a function between vector spaces that preserve vector addition and scalar multiplication. It can be represented as a matrix, making calculations easier. Common examples include identity, scaling, rotations, and reflections. Linear transformation have many practical uses. In computer graphics, to manipulate images. In physics, to model forces. And in engineering, for system design. That's all. Thank you for watching our presentation. We hope this gives you a clear understanding on linear transformation.